Okay, today's video is on graph analysis using integrals. So as you can see, we have a huge graph below our title, so let's get started. Number 1 says, given the function g of x equals negative 5x plus integral from 0 to x f of t dt, answer the following questions. And then A reads, find all the relative extremas of g of x on an interval negative 2 and 3, if any. So you can see that we outlined the interval on the graph right here. Okay, and then finding the relative extrema, we have to see, we have to first find the critical points of g of x, and then that probably means when g prime of x equals to 0, right? So first we're going to find g prime of x, right? Okay. And then g prime x equals negative 5, and then this goes inside because we're taking the derivative of the interval, so f of x. Yeah. And then we're supposed to find when this is equal to 0 to find the critical points. So when f of x is equal to 5, right? And on this interval, the only point where f of x is equal to 5 would be negative 1/2 and then 5. Or not negative, 1/2 and 5, right? So this is when x is equal to 1/2, right? So this is our critical point. Let's do a quick sign analysis to see if this actually is a relative extrema. So 1/2, right? And then let's see. Something less than 1/2 would be like 0, easy, right? So let's see if g of 0 equals something. So g of 0, g prime 0, is negative 5 plus f of 0. And then what is f of 0? F of 0 is 0. Okay, so we have negative, which means, okay, and let's try to find something that's greater than 1/2. Let's say 1. 1, we have 0 again. So negative 5 plus f of 1 equals negative 5 again. So this is still negative, right? So there is no sign change. So I guess we don't have a relative extrema for this question. Okay, so we're going to write a quick justification. So is no relative extrema of g of x on as the only critical point on the interval x equals 1/2, or at x equals 1/2, does not produce a sign change in f of, or no, not f of x, g prime x. Alright, so remember to always write a quick justification to show how you got your answer. Okay, and then it asks for points of inflection, which is associated with g double prime of x, right? Because concavity. So this is where concavity changes. So let's find g double prime of x, which would be not negative 5, because it's a constant. And then just f prime x, right? Okay, so derivative of f of x is f prime x, right? And then points of inflection is when the g double prime changes signs. But then, because g double prime is equal to f prime x, this is also when f prime x changes signs, right? And when f prime x is changing signs, like from positive to negative or negative to positive, that means that f of x is changing from increasing to decreasing and vice versa, right? So we're trying to find all the points where f of x is changing from increasing to decreasing and vice versa. Okay. And then this is on negative 2 to 1. So let's reset our boundaries. Oops. Our boundary is right here and then right here. Okay. So starting off from negative 2, it's decreasing, right? Decreasing, decreasing, decreasing until it strikes right here. And that is negative 1, and then it starts to increase, right? So here is 1 point of inflection, and then we're increasing, then we strike another point, and then we start to decrease until we reach x equals 1, right? So we have 2 points of inflection. One is at -1, and then that seems like 12.5. Okay, -12.5. And then we also have this one, 1/2 and 5. So those two will be our points of inflection because f of x, which is also f prime x, which is also g double prime of x, changes signs here. Okay. Alright, let's also write a quick justification right here. There are, or we can just say g of x has points of inflections -1, -12.5, and 1/2 and 5 as at these points. F of x decreasing to increasing, then to decreasing again. Yeah. Make sure to specify like which direction it's going. Like if it's changing from positive to negative, state that. If it's changing from negative to positive, also state that. If it's changing from decreasing to increasing, also state that, so it can really show and justify your answer. Okay, and in part C, use Euler's method with a step size of delta x equals 1 to approximate the value of g of 3, given that g of 1 equals 4 and f of 2 equals -18. So for this one, Euler's method, if you're familiar, it's best to make a quick chart, okay, and then we're going to say the x value, y1 dy over dx derivative, and then y2. And in this y2 value, you can calculate using dy dx times delta x and then plus your y1 value, and then this value will carry on to the y1 value of the next row. Okay, so first we're starting off with x equals 1, and then we have the value of y1 equals 4, and then dy over dx, right? So we can say g prime of x equals, what is it? -5 plus f of x, right? And then at x equals 1, this would be -5 plus f of 1, and then earlier we found that f of 1 was 0, right? That means it's -5. Okay. This one is -5, and then let's try to find a y2 value, which is -5 times subsize of 1 plus 4. So -5 plus 4 is -1, right? So for x equals 2, the y1 value is -1, and now we're going to go again to g prime of 2, because we're trying to find a dy dx again, and then that would be -5, and then plus f of 2, right? And then f of 2 is given right here, so we can plug that in. Okay, -18 equals -23. Okay, so this is the dy dx value for x equals 2. Let's try to find a y2 value, which is -23 times step size of 1, and then plus y1, and then y1 we have -1. So -1, we have -24. Okay, and then I mentioned that this value of y2 carries over to the next row's y1 value. So next row is 3 because the step size is 1, so it's incrementing by 1. So the y1 value of x equals 3 is negative 24, which means that g of 3 equals negative 24. And just to clarify, the reason why this part, f of 2, is specified is because the graph is cut out at this point when it's f of 2. So usually you will have all the values in the graph, but this one was a little bit special because it was cut out. Yeah, that's it for part A. Thank you.